Hello everyone, my name is Alroy Bonviaje and I'll be doing a presentation on cardiac output and how integrals are represented in this process. First, let's define what cardiac output is. Cardiac output is, in simplest terms, the volume of blood pumped by the heart per unit of time. So, in this process, there are two major time frames that we must distinguish. The first is when the heart relaxes. The second is when the heart contracts or squeezes. When the heart relaxes, blood flows into the right side of the heart through the superior and inferior vena cava. And on the left side, blood flows into the pulmonary veins on the left side of the heart. On the right side of the heart comes in deoxygenated blood, and on the left is oxygenated blood. So the second major function of the heart is when it squeezes or contracts. And when the heart does this, blood flows out from the right side of the heart into the lungs through the pulmonary artery. And on the left side, the oxygenated blood flows throughout the rest of the body through the aorta. One factor that influences cardiac output is oxygen content in the blood. So we'll see why this is important on the next slide. So how do we measure cardiac output? We can measure cardiac output through one method, which is the dye dilution method, which measures the concentration of dye in a liquid during cardiac output. So what this basically does is that the concentration of the dye, is supposed to mimic the oxygen content in the blood. So whenever we put in a liquid with a concentration of dye, on the other side of the heart comes out a liquid with another concentration of dye. So that's supposed to represent the change in oxygen as it enters the heart and as it leaves the heart. So the formula to represent this method is cardiac output equals the quantity of dye over the integral of the concentration of dye. Now, why is the integral needed for the dye dilution method? So as you can see here at the bottom of this function, it is the concentration of dye. So finding the antiderivative of this and finding it within this interval will give us a function in terms of milligrams times seconds over liters, which is basically concentration per unit of time. So why this helps us is because by putting this under the quantity of dye, which is represented in milligrams or other weight unit, would give us a numeric value that is expressed in liters per second, which tells us the liters of blood that is pumped per second. First problem. If the dye dilution method is used with 5 milligrams of dye, and the concentration of the dye in milligrams per liter can be modeled by the given function, find the cardiac output. Okay, so our first step is going to write the cardiac output function, which is quantity of dye over the integral between 9 and 0 times the concentration function, which is 1 over 3t. 1 over 3t times 9 minus t. And then with respect to time. So first we're going to isolate that bottom function. And so that will be 1/3 times 9t squared over 2 minus t cubed over 3. And that's already the antiderivative we have here, between 9 and 0. Okay. So next we're going to just input 9 into the function. And since inputting 0 would just give us 0, we're just going to get the answer straight from this. And that would equal 40.5 milligrams times seconds over liters. Okay, next we're going to input that into the cardiac output function, 5 milligrams over 40.5 milligrams times seconds over L. and that would equal 0.124 liters per second. And since those units cancel out, we got liters over seconds, and that will be our answer. And thank you for watching.